Hello, and thank you for taking the time to visit while I share information about modeling fire relationships with wildland housing intermix, invasive species, and land classes in the United States. My name is Brice Hanberry, and I work for the United States Forest Service at the Rocky Mountain Research Station. Frequent surface fire was the primary historical disturbance regime in many historical ecosystems of the United States. Surface fire is an understory disturbance that removes small diameter trees and fire-sensitive species and allows herbaceous vegetation to be competitive. Herbaceous vegetation is able to tolerate above-ground biomass removal, unlike trees. For the past century, surface fire has been excluded. Fire exclusion includes active fire suppression and also lack of deliberate ignitions plus land uses that break up fire spread. These land uses include impervious surfaces and land uses with limited dry vegetation such as croplands. Another land cover that reduces surface fire frequency is closed forests, in which trees replace herbaceous vegetation. In this case, surface fire frequency is reduced, but frequency of severe fires increases. This land cover of closed forest has a positive feedback because it is the lack of frequent surface fires that allows tree densities to increase, changing open forests of savannas and woodlands to closed forests. In the eastern United States, this process is called mesification, and in the western United States, this is often called fuel buildup or fuel accumulation. Prescribed burns were common practice before the 1900s as a management tool and also for prevention of high severity fires. However, frequent fires result in understocked forests and kind of waste of forest products, and so people favored a protection of forests from fire. Fire has been deferred for about a century, resulting in departure of fire regimes and ecosystems from historical ecosystems, increased tree densities, and escalating costs to fight fires, and also an information deficit about fire ecology. Today I'm going to briefly talk about three modeling studies. The wildland-urban interface occurs at the intersection of houses and undeveloped wildlands. Because there is no operational definition of wildland-urban interface based on where fires in fact have occurred, I use fire occurrences to objectively establish a definition of different classes of housing densities. Secondly, fires often are associated with invasive species. For the eastern United States and also eastern forests, I examined number of recorded non-native plant species compared to wildlife area adjusted for county area. Lastly, fire regimes have diverged from historical regimes, but historically fires were most frequent in herbaceous vegetation. I examined the importance of land class variables for fires. To model fire occurrences and housing densities, I used a wildlife occurrence dataset for the United States and the variables from the Silvis wildland-urban interface layer, which are housing and population densities and also vegetation cover. To model number of non-native species I used the Center for Invasive Species and Ecosystem Health dataset, and then I also use percentage area burned per county from the wildfire occurrence dataset. To model large fires and land classes, I use the monitoring trends in burn severity and geospatial multi-agency coordination databases with the National Land Cover Database. I applied random forest, extreme gradient boosting, and the C5 classifiers. For fire occurrences and housing densities, the classifiers performed well in correctly identifying fire occurrence. Fire occurrences overall were predicted for housing densities less than 100 houses per square kilometer, with a low threshold for percent vegetation cover. Population density was relatively unimportant. So generalized guidelines from this study are continued use of existing definitions for wildlands and the low housing density class. These classes have the greatest chance of fire occurrence. However, fire occurrences were predicted for census blocks with vegetation cover as low as 10%. Fire occurrences were predicted up to about 50 to 100 houses per kilometer squared, depending on modeled years and regions, and I called this range of housing densities the medium density class. The high housing density class is 100 to 200 houses per kilometer squared, and interface or really suburban communities are 200 to 400 houses per kilometer squared. Implications of revising the standard definition include a larger critical area classified as greater fire risk compared to the standard definition, specifically for the low density class, which has a high fire risk. For example, area of the low density class was 780,000 kilometers squared during 2010 compared to 530,000 kilometers squared, and therefore this revision incorporates more communities and homeowners into a high-risk status. Even though the housing density definition was the same, the vegetation cover had a lower threshold based on models of fire occurrence. In general, the new definitions have a more consistent range of housing densities. For the number of non-native species in fire, R-squared values were relatively high in eastern forests, with values ranging from 0.15 to 0.31 depending on the class of fire. However, this is a negative relationship, and the number of non-native species decreased with area burned. For the number of non-native species in fire in the eastern United States, R-squared values were relatively neutral. I didn't examine invasive species specifically, as there does not seem to be a definitive list. However, native invasive tree species definitely increase without fire. Species such as red maple and black cherry, ashes, elms, and eastern red cedar. And this has caused the state shift from open oak and pine forests historically to closed forests comprised of a diversity of tree species and fewer herbaceous plants. For large fires and land classes, the models performed well. Overall, greater abundance of herbaceous grasslands or herbaceous wetlands in the eastern United States and evergreen forest and low abundance of crops and pastures characterize most large fires. The 14 states in the northeastern United States with no or few large fires contained limited herbaceous area and in addition to abundant crops or developed lands. Regionally, herbaceous vegetation was the most important variable for fire occurrences in the western region, which is the dark green in the figure. Lack of crops was most important for fires in the central U.S. Lack of pasture, crops, and developed open space was most important for fires in the eastern region. Despite departure from historical fire regimes, these models demonstrated that herbaceous vegetation remains important for fires and that evergreen forests in particular are fire prone. Reduction of vegetation surrounding housing developments will help provide a buffer to reduce large fires. Coexisting with fire is one of the challenges of our time. The primary strategies are to identify communities at risk, then disclose the risk to the communities and homeowners, then reduction of fuels around structures and reduction of flammability of the structures is critical to prevent ignition. And planning and zoning can help reduce development in wildlands where fire risk is greatest. And along similar lines, also planning and zoning can restrict new developments to where risk is lower, for example, near land uses with reduced vegetation. In conclusion, it is important to realize that trees are a wonderful amenity, but increased tree densities are dangerous for fire risk, and also risk of, tree hazard falling due to insect, wind, or drought damage. Thank you for taking the time to listen, and if you have questions or comments, please contact me at brice.hanberry@usda.gov.